Here's a quick overview of what we'll be covering today. First, we'll start by understanding what an abstract class is, its definition and purpose in object-oriented programming. Next, we'll explore why we use abstract classes, focusing on how they help enforce structure, promote code reuse, and support consistent design. Then, we'll look at two real-world examples, the payment system and the vehicle system, to see how abstraction works in practical, everyday coding scenarios. Finally, we'll wrap up with a conclusion that summarizes how abstract classes help us build flexible, maintainable, and scalable programs. This flow will give you a clear and complete understanding of abstract classes, both in theory and real-world application.
Now, let's look at what an abstract class really is. An abstract class is a class that's declared using the abstract keyword. It acts as a blueprint for other classes but cannot be instantiated directly, meaning we can't create an object from it. What makes it powerful is that it can include both abstract methods, which have no implementation, and concrete methods, which contain actual code. This allows developers to define shared behavior in the abstract class while letting each subclass provide its own specific implementation. In short, an abstract class helps us build a common foundation for related classes, promoting structure, reusability, and clean code design.
And then let's talk about why we use abstract classes in programming. First, they allow us to define a common template for a group of related classes, ensuring they all share a consistent structure. Second, abstract classes enforce a specific method structure across subclasses, so each subclass must implement certain methods in its own way. Third, they help reduce code duplication by placing shared logic in one place, which also makes our code more reusable and easier to maintain. And finally, abstract classes let us partially implement functionality. We can define some behavior in the parent class while leaving the finer details for subclasses to complete. In short, abstract classes provide both consistency and flexibility, which are key in good object-oriented design.
Let's look at a real-world example, the payment system, to understand abstraction. Imagine different types of payment methods, such as credit card and PayPal. Even though they work differently, they still share a common process, making a payment. To model this, we create an abstract class called payment. This class contains a shared property, amount, which represents how much needs to be paid. It also defines an abstract method, pay, which forces each payment type to implement its own version of the payment process. At the same time, payment includes a concrete method, payment details, which displays the shared information for all payment types. This structure allows us to keep common logic in one place, while still giving each payment method the flexibility to handle payments in its own unique way. A perfect example of abstraction in action.
Now, let's look at another real-world example, a payment system. Here we have an abstract class called payment. It represents the common structure for all types of payments. Inside this class, there's a common property, amount, which stores how much needs to be paid. The constructor initializes this amount whenever a payment object is created. Then we have an abstract method, pay, which means each subclass, like credit card payment or cash payment, must define its own specific payment process. Finally, there's a concrete method, payment details, that displays shared information such as the payment amount. This structure allows consistency across different payment types while still giving each one the flexibility to handle transactions in its own way. Now, let's look at another real-world example, a payment system.
Here's how we bring the abstract payment class to life with a real-world subclass, credit card payment. This class extends the payment class, meaning it inherits the common property amount and the shared method payment details. We then add a new property, card number, which is specific to credit card transactions. In the constructor, we call super of amount to pass the amount to the parent payment class, and we store the card number for this transaction. Next, we override the abstract method pay, providing a concrete implementation that prints a message like paying $100 using credit card 1234.
Now let's look at another subclass, PayPal payment, which also extends our abstract payment class. This class introduces a new property, email, representing the user's PayPal account. In the constructor, we call super amount to initialize the common payment amount and then store the PayPal email for this specific transaction. We then override the abstract method pay, giving it a unique implementation. It prints a message like paying $100 using PayPal account example@email.com. This example shows how each subclass, whether it's credit card payment or PayPal payment, follows the same structure from the abstract class, yet performs its own distinct payment process. It's a great demonstration of how abstraction helps build flexible, reusable, and well-structured code in real-world systems.
Finally, let's see how everything connects in our payment demo class. In the run method, we create two objects, a credit card payment and a PayPal payment, both derived from the abstract payment class. Even though payment itself can't be directly instantiated, it serves as a common reference type, allowing us to treat all payment types in a unified way. We first call payment details to display the shared information, such as the payment amount, and then call pay, which performs the specific payment process depending on the subclass. This example perfectly demonstrates abstraction and polymorphism in action, one abstract class defining the structure and multiple subclasses handling their own unique logic. It's clean, flexible, and easy to extend for future payment methods. Let's look at a real-world example. A vehicle system. Imagine different types of vehicles, like a car and a bike. Both share common traits, such as having a brand and a year, but they start in different ways. Here, we can define an abstract class called vehicle. This class includes common properties like brand and year, and an abstract method called start engine, which forces each subclass, like car or bike, to define how it starts. We can also include a concrete method, show details, to display shared information about the vehicle. This design keeps our code organized, promotes reuse, and ensures every vehicle type follows a consistent structure while allowing unique behavior where needed.
Here's how we can model a vehicle system using an abstract class. We start with an abstract class named vehicle, which represents the common blueprint for all types of vehicles. It has two shared properties, brand and year, and a constructor that initializes these values when a vehicle object is created. Next, we define an abstract method, start engine, which means every subclass, like car or bike, must provide its own specific way to start the engine. We also include a concrete method, show details, which displays the brand and year, something common to all vehicles. This structure ensures consistency across different vehicle types, while allowing each to define its own unique behavior. It's a clear example of how abstraction keeps our code organized, reusable, and easy to extend.
Now, let's see how we can create a subclass from our vehicle abstract class. Here's the bike class. The bike class extends vehicle, meaning it inherits common properties like brand and year, as well as the shared method show details. In the constructor, we call super brand year to initialize these values using the parent class. Then we override the abstract method start engine, providing a specific implementation for bikes. In this case, it prints a message like Yamaha bike engines started with a button. This example shows how abstract classes define a common framework, while subclasses like bike add their own unique behavior, keeping our design both structured and flexible. Here we have another subclass of the vehicle abstract class, the car class.
Just like bike, the car class extends vehicle, so it inherits the common properties brand and year, as well as the shared method show details. In the constructor, we call super brand year to initialize those values from the parent class. Then we override the abstract method start engine, providing a version that's specific to cars. Here it prints a message like Toyota car engine started with a key. This example clearly shows how abstraction allows different types of vehicles to share a consistent structure while defining their own unique behaviors. It's a simple yet powerful demonstration of code reuse and flexibility in object-oriented design.
Now, let's bring everything together with our vehicle demo class. In this example, we create two objects, a car and a bike, both derived from the abstract vehicle class. Even though vehicle itself can't be instantiated, we can use it as a reference type for its subclasses. Inside the run method, we call show details and start engine on both objects. The output demonstrates how each subclass provides its own version of the abstract start engine method, while still sharing the common show details behavior. This shows the real power of abstraction and polymorphism. Different vehicle types following one current structure, but behaving uniquely. It's a perfect example of clean, reusable, and extendable object-oriented design. Now, let's bring everything together with our vehicle demo class.
In the end, to wrap up, let's summarize what we've learned about abstract classes. Abstract classes provide a strong foundation for creating similar types of objects. They help promote code reuse and maintain a consistent design across different parts of a program. They also allow for partial implementation, giving flexibility for subclasses to add their own specific details. In real-world systems, abstract classes are commonly used in vehicle systems, payment processing, and user interface components where shared behavior and structure are essential. Overall, abstract classes help us build software that's organized, reusable, and scalable, making them a key feature of good object-oriented programming.